Time to combine what you've learned about nucleic acid extraction chemistry and liquid handling robotics. There are 6 core steps to most automated nucleic acid extraction workflows using magnetic particles. 1. Lysing and digesting your samples. 2. Binding free nucleic acids to the magnetic particles. 3. Magnetizing the particles. 4. Washing the particles. 5. Drying the particles. 6. Eluting the isolated and purified nucleic acid from the particles. There are many variables to optimize in these 6 steps. However, if you develop each step incrementally using your manual extraction method as a control and optimize each step in sequential order, this process is much more manageable. After each step or series of steps with the robot, finish the extraction manually. This will let you assess the quality of the automated step compared to the manual control. You can save time if you visually inspect that the basic criteria are met at each step. For example, make sure particles are suspended during a binding or wash before moving on. When yield and purity are lower than what you would get with the manual method, then you must optimize the most recent automated step. If the yield and purity are acceptable, you can move on to the next step in the workflow. And as you optimize, always keep your process requirements in mind. It's easy to over-optimize steps that will not greatly influence the extraction workflow outcome or your downstream application. But losses in yield also compound over multiple steps. You'll need to decide what is an adequate balance. For example, consider optimizing liquid handling for whole blood samples. Because the samples are typically viscous, a 5 to 10% error in pipetting volumes may be an acceptable performance compromise, but dripping that contaminates other samples is not. Now, let's discuss other tips that will help you address the most common challenges in each of the 6 automation steps. If you're using an extraction kit, follow the recommended steps. Order of addition can seriously impact extraction performance. For example, you should only add proteinase to your sample or a mix of your sample and digestion reagents. Adding proteinase directly to digestion reagents will reduce the efficiency of the lysis and digestion step. Temperature is also critical. Keep an eye on your samples. Unexpected cloudiness or viscosity compared to your manual control may mean the temperature is too high. This step is all about mixing. Make sure that particles, also referred to as beads, are fully and evenly suspended throughout the sample. If you're using a shaker, watch and make sure a vortex is fully formed. For viscous liquids like blood, it might be hard to resuspend particles once they settle. Starting the mixing before adding the magnetic particles can keep the particles suspended. During the binding step, volumes are often large, and max RPMs for vortex mixing cannot be used. If pipettes do not drip during transfers, splashing during the binding step is the most common cause of well-to-well cross-contamination. A standard 2 milliliter well plate can typically handle 1 to 1.2 milliliters of liquid before cross-contamination during mixing becomes a problem. If throughput and your robotics setup allow, you can also mix by pipetting. Immobilizing the magnetic beads is controlled by 3 parameters: the position of the magnets, the amount of magnetic field applied, and the quantity and size of magnetic particles. Watch the beads during this step. Make sure they're fully collected. Magnetizing the post for 1 to 3 minutes is typically enough. If you are using a ring magnet, make sure there's a clear gap in the center of the well for the pipette. If there is not a clear path for the pipette to the bottom of the well, reduce the number of beads in your extraction. If you find that the absorbance ratios of your samples decrease while optimizing the washing stage, that's a sign impurities weren't fully washed away. Your method will likely involve several washes. The first is the most challenging and most important to optimize. There are many proteins in the sample at this point. These proteins can cause the beads to aggregate and trap impurities. The magnetic particles must be fully resuspended to release and wash away these impurities. Good mixing is crucial. Try increasing the shaker speeds to improve bead suspension during the first wash. Volumes should be low at this stage, so the risk of splashing is low. If you do need to mix by pipetting, consider using a particle mover robot or a 96-channel pipette on the platform. If you only mix 8 wells at a time, your throughput will drop dramatically. If faster mixing doesn't improve bead suspension, Try washing the sample with water or TE buffer and mixing vigorously. This elutes nucleic acids from the beads and breaks aggregates. Rebind the nucleic acids by adding binding buffer at the exact ratios used in the binding step. If the beads are fully suspended during the wash step and you still see low purity, there might be a problem with liquid handling on the robot. If the robot does not fully take up supernatant during the wash steps, impurities can persist. You can adjust liquid transfer volumes. You can also add another wash to dilute the lingering contaminants. Use a polar, non-viscous solution like 80 to 95% ethanol or the solution used for the recommended final wash. Follow the kit manufacturer's instructions or your manual protocol for drying. Drying at room temperature is slower, but tends to give consistent results. Higher temperatures accelerate drying, but can over-dry particles and give lower yields until optimized. To maximize processing speed, you will likely need to optimize the temperature and timing of this step. Elution is only affected by a few parameters: mixing and temperature. In general, heated elution is not necessary, but it can improve yields. The most important element in this step is effective mixing for at least 1 to 3 minutes. Let's summarize. There are 6 stages to an automated magnetic particle-based nucleic acid extraction. You can efficiently optimize each of these steps by taking an iterative and informed approach. Knowing the chemistry and robotics of the workflow can help you troubleshoot any one of these steps and create an automated workflow that meets your quality and throughput needs. Explore our Automated Nucleic Acid Extraction Resource Center and check out our experimental design and troubleshooting guide to find more information and tools to support your workflow development.